Howdy everyone, and welcome back. And we're going to continue talking about electromagnetic radiation. We're going to keep talking about light and some of the applications for it. We talked about the basics of light, but now we want to sort of get into some of the applications and what we can do with light, and basically the subtopic of optics, which ends up being a whole field in physics to itself. But again, we're always going to get just a sampler and taste of things. Today we're going to talk about a couple of rules, one of them being the law of reflection, which hopefully we should be somewhat familiar with, and the law of refraction. So how reflection is light bouncing off of mirrors and reflective surfaces, and refraction is it bending through different mediums like water and glass. So let's go over that mathematically. What does that look like? And we'll do a couple problems. Here we have the law of reflection. So we have light coming in from some angle, and we usually measure the angle in optics. And what we're going to do today from the normal of a surface. So you have a surface, and the normal vector is the one that points out perpendicular to each side. So light coming in comes at some angle. The law of reflection saying if this is some mirror, this is some reflective surface, these two angles have to be the same. And we should be somewhat familiar with that, with using a mirror around our house. Light bends off and it's the same angle comes in. Hopefully that seems somewhat familiar. So refraction is a little bit weirder. It's not exactly as intuitive, but it will make sense if we talk about this for a little bit. So we have light coming through some material. It has some type of index of refraction. So an index of refraction we define as the speed of light in a vacuum over the speed of light in a material. So light has some maximum speed in a vacuum, but it can slow down in other materials. And so this law of index of refraction is always going to be a value either equal to 1 or greater than 1. But because the speed is different between two of them, we'll find actually that these two angles aren't going to be the same necessarily. In fact, they have to be different if the index of refractions are different, given by Snell's law, which is n1, the law of refraction of the first, times the sine of this angle has to equal, the same stuff, but for this other side. So this may seem a little bit weird, but I want to connect it with something that maybe we can think about in our everyday life. So imagine you have an area of sand here, and you have some water out here. So you have a guy who needs to be helped, maybe drowning in the water. You have a lifeguard sitting over here, and he needs to get to him, and needs to get to him in the quickest time possible. So you may think that the quickest path is just to go straight beeline to him, but it turns out it's actually not the quickest path, and you can time this out if you really wanted to. But it's actually to run a little bit more along the water, well, not the water, but run a little bit longer across the sand and then turn into the water. Turns out this is actually quicker. So the same sort of thing is going on with light over here. So light's not bending because of any special or magical reason. It's actually because light is taking the path that takes the least amount of time to travel through. We actually have a special name for these sort of paths that particles and other things we usually move in. They're called geodesics. And geodesics are just paths where something is moving in an optimized way. There's something that's being optimized, usually time, but could be other things. So light is bending because it's taking the least amount of time possible. That's all that's going on. So let's do a couple problems. Let's get a handle of this. Especially let's focus on Snell's law here. Here we have light coming in here, and then it's getting bent over here. So over in this region we have air, and over here we have some type of other material. So we're saying, okay, if it's fused quartz, how much is it bending? So air essentially, regards to light, is effectively a vacuum. It's so low density that the index of refraction is effectively 1. We're told the index of refraction of the second material over here, and we're told this incident angle is 45 degrees. So how do we get the second angle? Well, we use Snell's law here. So we write down Snell's law, and we need to solve for this theta 2. So we can divide out n2 to the other side. That's this equation. And then we can take the inverse sine of both sides. And we take the inverse sine of this, it gets rid of the sine, so it's the inverse function. And we're just left with actually a bunch of stuff that you can just straight put in your calculator. N1 over N2, okay, we know these numbers, sine of theta 1, and then we can use this inverse or arc sine function. We put that in, we find that the second angle is going to be 29 degrees. So it went from a smaller index of refraction to a larger one, and the angle got a little bit smaller. Okay, and they were asked to do the same thing. What if it's something else? What if it's carbon disulfide? So as long as we have this index of refraction here, we can go and solve for this same thing. We put this new number, this new n2 into this equation, and we can go and solve for it. Now it's 25.7 degrees. Okay. Then maybe we ask, what if it's water? So, water has a net index refraction of 1.333, or, so go in, put in the same equation, and we get theta 2 again. Nothing crazy, nothing really mysterious. I don't think anything hopefully too challenging yet, but let's keep going. So let's do a problem where we have more than one material change. So we can see the trajectory of light gets bent and then it gets bent again. So there's 3 materials. So we're gonna have to split this into essentially 2 different problems. One where we care about this boundary here, and the other one where we care about this boundary here. So we can do that. So the first thing is we're told that this is air, so the index of refraction is 1, and this is glass, index of refraction is 1.5. So first thing, we want to find this second angle here. So we can do what we did in the last problem and essentially pull that equation and get this angle, 19.5 degrees, okay? So now we want to find this third angle, so it bends here, and we get a third angle that pops out here, and we're told that it's also going to be air. So we go and put it through the same sort of equation and stuff, but we sort of notice that in the end, you can double check this if you want, but it turns out it's going to be the same angle as that we had here, we're going to have down here, because it turns out they have the same index of refraction, so the angle has to be the same. But you can always put in this stuff, try it again on your own. Put in this for theta 3, put in all the numbers regards to this boundary instead, you'll find that this ends up being just 30 degrees. Okay, and then we can find, since this light just got offset a little bit, now how much did it get offset? So we can imagine it kept going straight and it's parallel with this line here, but it just got offset an extra distance d. Maybe we want to figure that out. And looking at my notes now, I realized I made a mistake when doing this, but you can do this by looking at the triangles here. So we have this distance is 2 centimeters here. So we look at this triangle here. This is actually going to be, I realized I made a mistake, 2 centimeters tangent theta 2. And here we look at this triangle. This is going to be 2 centimeters tangent theta 1. And then this distance is essentially just going to be the differences between these 2 distances. So we just put those in. I think it turns out tangent and sine are relatively close for small angles, but I think the real answer may be off by a little bit compared to this, but we can keep going. Maybe ask, what's the speed of light in a glass? So then we can go back and use the definition of an index of refraction where n equals c over v. We go solve that and put the index of refraction on the other side and multiply the v onto the other side. So essentially we can get the velocity is just the speed of light over the index of refraction. Index of refraction for glass is 1.5, so the speed of light that's moving is 2 times 10 to the 8. So maybe we want to figure out how much time does it spend going through this block. So we can draw this distance that it goes, this d at this angle, theta 2. We know this is 2 centimeters, so we can write out the hypotenuse as 2 divided by the cosine here. So the cosine is going to be the opposite over the hypotenuse. We go write out the hypotenuse, 2 centimeters over cosine. So 2.12 centimeters. So now we know that distance, we got the velocity from this last problem. So it was in there like 1/10 of a nanosecond, so pretty much instantaneous at at these sort of distances. The angle that it came in here, it could have done like this, it gets bent. It's always going to end up with the same angle here. So the distances are going to be a little bit different in here, but it's always going to come out at the same angle, but just shift it over a little bit. So maybe we had some application where we want to just move light horizontally. This would be a good, way to do that. A quicker topic. I think that's all I want to get to today. Thanks as always for joining me. Really appreciate it. Okay,